Hello there. I'm continuing with these multiple choice problems from the Barron's book. I actually started to make this video a few minutes ago and took pictures of the wrong problems. So as I go through, I'll remind you some of these problems really aren't quite right in terms of what's on the AP. All right, let's look at 16. So the graph of G is shown above, and the graph of f is shown above. Capital G is defined as the definite integral starting at 0. Capital H is defined as the definite integral starting at 2. Which of these are true? So one thing I want you to just kind of have on autopilot from the second part of the fundamental theorem of calculus. Once I see that, right, I'm starting at a constant and ending at x. The rate at which G changes is f. And for the same reason, the rate at which h changes is f. But that's not quite a choice. Another way of thinking about this is G is mentioned. So let's suppose X is, say, here. G is measuring this total integral, that net signed area in purple. H is only measuring this part. So what we might notice is that G is just all this extra stuff. This area here is 3. So when you measure G, it's starting with 3 and then doing this integral. So that would be D. D is like H, but 3 bigger. They have the same derivative, right? You'll notice the derivative here is the derivative here. All right, 17, minimum value. Minimum value for a continuous function on a closed interval occurs at an endpoint or a critical point. So let's take a derivative. F prime of x for this one is 2x minus 2x to the negative 2. I'm just interpreting this as x to the negative 1. If I set that equal to 0, right, we don't have to worry about x equals 0 on that interval. I would have 2x equals 2 over x squared. So what does that tell us? 2x cubed equals 2 and x equals 1. That's our critical point. So we can just plug stuff in. We have an endpoint at 1/2. We have a critical point at 2. We have an endpoint at 2. So x squared plus 2 over x. Plug that in here. That's 1/4 plus 4. Plug in 1, I get 1 plus 2. Plug in 2, I get 4 plus 1. So the minimum of those is 3. Right, minimum value, not the x-coordinate where it occurs. For 18, which function could be a particular solution to the differential equation whose slope field is shown above? So if I were to graph these, which one would follow the slope field? And they're intentionally not telling you the scale, because they don't want you to do it by plugging in particular numbers. They want you to know what a graph looks like. So sine of x is a wave. We'll notice that this gets steeper in the middle in the way that a wave wouldn't. A wave would never have one portion that's particularly steep. It would just repeat all the same steepnesses. Pardon me. E to the negative x squared is a graph that looks like this. That's the bell curve, which is not what we're seeing here. Right? And also, you just note that this is an even function. We're not seeing an even function here because an even function would have balance across the y-axis, and we're not seeing that. We're increasing there. Similarly, b is even, so by process of elimination, it has to be a. This isn't, on the actual AP, they're not expecting you to so quickly know what these things look like. But you do need to understand the relationship between graphs going through a slope field. All right, next page. Yeah, another thing where maybe you don't need to know this. Which of these functions could have a graph like this? Right away, I'll point out that this thing here is undefined if x is negative 1, but we don't seem to be seeing that. X equals negative 1 would determine if this is positive or negative. This is an odd function, but the graph doesn't have symmetry, so it's not that. So it's down to either A or B, and we could think about derivatives. For A, if I take the derivative by the product rule, derivative of the first times the second plus the first times the derivative of the second, we'll notice that the critical point occurs at x equals -1, which is not what we're seeing here. Here, the critical point is x equals some positive number. So it's probably B by process of elimination. You could check there that the derivative looks like this. So the critical point would be at 1, and you would, if you made a sign chart, it's the derivative is positive before 1 and negative after 1, so it is B. 20, 21, and 22 all refer to this graph of velocity. They say velocity, they label it V. That's not a trick, but sometimes people just don't read. So for how many values in the open interval from 0 to 6 is acceleration undefined, right? And they're clear that it's open. They don't want you debating what happens at an endpoint, does that count or not? So acceleration is the derivative of velocity. This velocity graph would not have a derivative if there's an abrupt change in steepness. And that happens at 3 and 5. So there are two places where acceleration is undefined because of an abrupt change in steepness of the graph. When is the speed increasing? So speed is the absolute value of velocity. And you can think that increasing speed means velocity is moving away from 0. Right? Velocity of 0 means you're not moving. So if velocity is moving towards 0, you're slowing down. If velocity is moving away from 0, you're speeding up. So between t equals 3 and t equals 5, velocity is moving away from 0. Average acceleration? Well, acceleration is the rate at which velocity changes. So one way of viewing average acceleration is that it's the average rate of change of velocity. So that would be v of 5 minus v of 0 over 5 minus 0, which is -2 minus 3 over 5, which works out to -1. Number 23, another one of these pre-calc kind of problems that wouldn't likely show up on the actual test. Hopefully you remember that assuming something is reduced, vertical asymptotes occur when the denominator is 0. This denominator is 0 at x equals plus or minus 2, so there are two vertical asymptotes and D is the only possible choice. You can also confirm that in the long run there, y equals -2 is the horizontal asymptote. Okay, and now the last page. Did I take the wrong picture? I've been having the weirdest time just taking the right pictures. But let's do that now. This. Make it bigger. Okay, 24. So we have this piecewise function. So we're asked questions about continuity and discontinuity. All of these individual formulas are nice, but weird things could happen at the transitions. So let's think about what's going on near -2. So near -2, x squared is approaching 4, and it's 4 on the other side. So we don't have a discontinuity at -2. This is approaching 4, this is 4. How about at 1? On one side of 1, it's 4. On the other side, it's 6 minus x, which is approaching 5. So there's a discontinuity at 1. So what do we got here? Not continuous everywhere. Discontinuous only at one looks right, but let's read the others. C says it's discontinuous in 2 places. D says we have to fill stuff in. So, oh, okay. So there's a trick here, and I fell for it. This is a poorly constructed question, which would not be on the AP. Technically speaking, it's not defined at -2, so right away it's discontinuous there. So it is discontinuous at both of those places, but for different reasons. For one of those, so if we were to graph this, we have portion of a parabola, a hole, and then it's equal to 4. And then there's this jump to a line. So there's a discontinuity here because of the jump. Here it's simply because it's undefined. I don't think you would have something like that on the AP because this really does feel like a trick. Okay, number 25. So they give you this function f and they tell you it's on the point 1, 2. Here's the inverse. What is the derivative of the inverse at 2? So we need to think about corresponding functions. F of 1 is equal to 2. So f inverse of 2 is equal to 1. What's the derivative here? The derivative of f at 1, well, f prime of x is 5x squared plus 5x to the 4th plus 3, which is 8. So the corresponding derivative of the inverse at 2 would be the reciprocal of that, which is 1/8. Okay, 26 is kind of a tricky U substitution integral. I'll do this one formally. So it's the definite integral from 1 to e of the natural log of x cubed over x. If I'm copying this correctly. So what we might notice is natural log of x feels like the inside of a chain rule type thing. If I take the derivative there, that's 1 over x. So du is the same as dx over x, which conveniently is in here, right? An x in the denominator means what we really have here is the integral from 1 to e of natural log of x cubed times dx over x. Let's note that these bounds were for x. So if x is equal to 1, u is its natural log, which is 0. If x is equal to e, u is its natural log, which is 1. So if I make all those substitutions, u is now going from 0 to 1. Natural log of x cubed is u cubed, and this is du. So this is a very easy integral to do. And we get 1/4 times 1 minus 1/4 times 0. Our answer is 1/4, which is A. Another one of these questions that I think gets asked too much in these Barron books, right? They're more pre-calc questions about graphs, right? What can you say about a graph without actually graphing it? Let's notice this is an even function. If I plug in positive and negative x, I get the same thing. So it will be symmetric to the y-axis. Does it have a local minimum at x equals 0? Well, you'll notice that the inside is smallest at x equals 0. And natural log is an increasing function. So whenever the inside is smallest, natural log is smallest. So that's true as well. So 2 is also true. Now in terms of the inflection points, we just have to roll up our sleeves and take some derivatives. An inflection point is where the second derivative switches sign. So we have y equals the natural log of 4 plus x squared. First derivative by chain rule is 1 over 4 plus x squared times 2x. Then I'll need to take another derivative by quotient rule. So y double prime, so derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. If I work through this, in the numerator I have 8 plus 2x squared minus 4x squared. That's 8 minus 2x squared. Can factor out a 2 there, 2 minus x, 2 plus x. We'll notice that the denominator is always positive. So this second derivative switches signs at 2 and negative 2. So yes, those are where the inflection points occur. That's a lot of work to do in 3 minutes, but they're all true. Three more to go. Okay, so they're telling us that when we take this definite integral, we get x sine pi x. What can we say about f of 3? Let's copy this one. Right? They get harder towards the end. This one is not a problem you'll see a lot of. Some of these are standard problem types. This problem kind of, oh, that's not what I want to do. I just wanted to copy the one thing. So can I just copy this picture? No, not insert last image. Undo, undo. Now I see what happened. Let me try this again. Okay, let's just take a picture of number 28. Copy this. And then paste it. There we go. Okay, so this is very abstract. But what we'll notice is this familiar form. We have this familiar form, which is a function defined using a definite integral. So what we know is that if I were to call this, say, g of x, what we know is that the derivative of g is the function inside. Well, on the one hand, it's g of x, but on the other hand, that's what it is. So we can think g of x is x sine pi x. Now, on the one hand, if I take derivatives here, g prime of x, well, I can do this one using the product rule and the chain rule. Derivative of the first times the second, plus the first times the derivative of the second. But I also know that the derivative of this function, just from its form, is f of x. So f of x is this function. So let's just plug in 3. F of 3 is sine of 3x plus 3 times cosine of 3x times pi. And you do need to know basic trig values. Sine of 3 pi is 0. Cosine of 3 pi is negative 1. So this is 0 minus 3 pi, which is negative 3 pi. Our answer is A. Okay, 29. Integrals are defined as limits of Riemann sums. We need to make sense of what is getting measured here. So you kind of want to interpret this as values of a function times widths. So one thing I'll point out right away is we're adding together n things, and each one has a width of 1. So we can just make a little note that the total width is 1. Each one has a width of n, there are n of them, the total width is 1. So that's consistent with all of these. All of these are integrating over some interval with a width of 1. Now let's think about the values we're doing here. So if I start with k equals 1, So what is the range of values? K equals 1. If I plug that in, I would be computing the square root of 2 over n plus 3. Now let's keep in mind that n is approaching 0. So n is really, really big, which means 2 over n is really, really tiny. So this is roughly root 3. If I plug in k equals n, right, k starts at 1 and ends at n, then I have 2n over n plus 3. 2n over n is 2. I have the square root of 5. So what you can think is that the values that I'm plugging in here basically start at 3 and end, sorry, they start at the square root of 3 and they end at the square root of 5. So we can go through and look at those choices, and which one involves taking function values that start at the square root of 3 and end at the square root of 5. This one goes from root 6 to root 8. This one goes from root 3 to root 5. That looks promising. This one goes from root 0 to root 2. This one goes from root 9 to root 11. It's got to be B. And then finally, looks like we've got a volume problem. So we have the region bounded by y equals e to the x. Let's draw a rough picture here. Y equals e to the x looks something like so. Y equals 1 is a horizontal line. And x equals 2 is a vertical line. So this point right here is occurring at, sorry, let me redraw this better. I think you would get a picture for this on the AP. In the Barron's book, they're really trying to give you hard problems. So I'm going to change my scale here. So y equals e to the x, something like so. Y equals 1, so that's actually where this this x-intercept is at 0, 1. So y equals 1 goes straight through there. And then x equals 2 is a vertical line like so. So we have this region here. This is y equals e to the x. This is y equals 1. And we're going to rotate that about the x-axis. What is the volume? So the idea is, right, the general principle is we find volume by taking a definite integral of the area of each slice. And here we'll slice this with x's. So here's my x-axis. As I move along, I can think, all right, at some x value, I have this getting spun around. X starts at 0 and ends at 2. What is my shape? Well, here's a point on the x-axis. This is the center of the disk, of the washer. We're spinning this around, we get a washer. Area of a washer is pi times the big radius squared minus pi times the little radius squared. That big radius is the distance from the x-axis up to the top graph, which is e to the x. The smaller radius goes from the x-axis to y equals 1. That's just 1, and 1 squared is 1. So we are taking the definite integral from 0 to 2 of pi times e to the x squared, which I'll write as e to the 2x, minus pi. What's our antiderivative? Well, e to the 2x is kind of its own derivative and its own integral. But if I took the derivative of that, there would be an extra 2 that I want to cancel. So you can check. If you take the derivative of this by chain rule, you get pi times e to the 2x. Pi is a number. The derivative, sorry, the antiderivative of pi is pi times x. So if we plug in 2, we get pi over 2 times e to the 4th minus 2 pi. If I plug in 0, I get pi over 2 times 1, because that's e to the 0 minus 0. So pi over 2 e to the 4th minus 2 pi minus half a pi. Those are like terms, so that's 5 halves pi. So is this a choice? Oh, and I did an extra step because I didn't bother to read. So we'll see that this is C. They factored out the pi, but this is the integral we're doing. Because I had to shift my attention, I didn't see the problem. On the true AP, there's plenty of space next to each problem, so you're not going to lose sight of it like that. You will be able to see it and realize, oh yeah, they just want me to write the integral. I don't have to do the answer. All right, that is the end of